really close to work. So we finishing the story about the rotations, specifically reviewing the partition function, right? You help me with it, and also getting the internal energy for the rotational part and the, what do we call this, CV? What is this? What's the name of this guy? Heat capacity. What the V symbol or whatever subscribe means. It's taking a volume constant. And then we move on to the vibrations. And again, the strategy to use the model from quantum mechanics. For vibrations, the model would be what? What is the model which describes the vibrational motion in molecules? What does it do? Yeah. So the model is harmonic oscillator, right? Because the molecules do oscillate. It's a motion, vibrational motion, oscillate, kind of very similar to the oscillations, which actually this is why we use the oscillator model. The model of the harmonic oscillator. And if you have enough time, right? So the strategy is to derive the formula using this. Well, the quantum mechanics gives us the information about the energies. Knowing energy, we put it into the partition function by definition, right? So which is the sum of exponents in the power minus energy divided by dt, energy of the states, and then sum over each of the states. And then our goal would be to figure out how to take the sum, right? And we already practiced vibrations, if you remember, long ago, on the second, maybe third week in the semester, when we were talking about Boltzmann distribution, we actually were working with oscillators, right? And we were already taking the sum. So just to be a review for you, the trick which we use, actually the sum in this case, you don't need to assume that the sum should be changed to the integral, because in this case, sum can be taken as a sum, because it's a well-known Taylor expansion, whatever the name of this well-known mathematical expansion. So which we know how to take the sum. And after we know the partition function, the strategy would be apply the formula which connects the partition function to the energy. And you should help me with this formula. I'm not sure whether you can see anything on this board. So what's the connection between the internal average energy and the partition function, molecular partition function? What is the formula? No, how it depends on the partition function. And I think nkt squared, right? And then you take derivative over ln, or you can write it as 1 over q, and then derivative with respect to the temperature of the q. Right? So which means, if you know q, if you know how q depends on t, you take the derivative, apply this, you know the partition function. And you know the internal energy from the partition function. And to find the CV, yeah, this is even simpler. You just take the derivative with respect to the temperature from u, which also depends on temperature. So first you find this function, right? Taking derivative, you get into the Q capacity. And yeah, this is vibrational, 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 because we're talking about vibrations. But before going to the vibrations, let's start with rotations first, right? Finishing the same story for the rotations. And you need to remind me what is the partition function for the rotations in its shortcut version. Something really two letters, well, actually 3 letters. If you have this sigma, which is a symmetry number, you need to figure out, we talk about diatomic molecules right now. So you need to figure out whether this is homogeneous or heterogeneous, means your diatomic molecule, let's say, having the same type of atoms like iodine 2, or it's different atoms, like, for example, iodine H molecule, right, or chlorine H. So then if it's different atoms, like HCl, for example, right, sigma would be equals to just 1, right? But if it's the same, then kind of was a, you can't really distinguish between this and that position in this case, right? That's why sigma would be 2. So it's a symmetry number, which is simple to remember. But what do we have on the top and on the bottom? Temperature on the top, right? And here, it's another temperature which we call rotational temperature. And it's characterized a molecule. This is for rotations. So what is the rotational temperature? Equals to HCV over what? K. Can I just, which units, if I'm using this formula, which units you use for H, C, and K? And for B? For all of them wave numbers? For B is a wave numbers, yes. And again, this B is a rotational constant which depends on the moment of inertia and other, actually mainly it's a moment of inertia, but we know moment of inertia depends on the reduced mass, which the mass kind of, including both masses of both atoms in a diatomic molecule, and the distance between them. So it's reverse proportional to the mass, to the reduced mass. What about these guys? If you write this formula, you expect which units to use for H, C, and K? Let's start standard or not standard units? Standard units. So means K would be joules per Kelvin, H would be joules times second, right? And C is the speed of light, meters per second. Or you also can represent this, and this might be very useful, especially for the exam, if you want to reduce your time for doing all these problems for practical point of view, right? You can, I will present it in this way, right? Putting tilde, saying that if you use both B and K in the wave numbers, you don't need to worry about this HC, because HC, the Planck constant times the speed of light, is just the units, the term which transfers the units from wave numbers to the standard units. But if we take this, right, this is wave numbers, of course, over Kelvin, right? So which means you don't need this HC because wave numbers are gone, and then you get in the answer in kelvins. That's why it calls rotational temperature, because it has a units of temperature. So here it's units of temperature, sigma doesn't have any units, right? Your Q doesn't have any units as we expect. So just a note, if you, probably from practical point of view, it's easy to take K in the wave numbers, if B is given in the wave numbers, right? And then you don't need to multiply by HC. But if you want, if you use standard units, then you need to convert your B to the standard units, to the joules, right? Which means you need this HC as a conversion factor. Makes sense. Okay, but for us, what is important is this part. Now, following the strategy, finding first U, then finding CV, what would be the U rotational? So I just apply this formula, NKT square. And don't worry, if you cannot see the whiteboard, I have a next slide with all these formulas. NKT square coming from the beginning. Is it KT square or NK? Yeah, it should be NKT square. Then 1 over Q means I just reverse this guy, right? So what was on the bottom goes to the top, because I divide by this. What was on the top goes to the bottom. So then sigma Q R goes to the top, temperature goes to the bottom. Now I need to take a derivative from Q. Well, this is simple. What is the derivative? 1 over sigma QR. Then what happens? Sigma is gone, QR is gone. This temperature also cancel out, and the answer for UR is just NKT. Yes? Then what would be the heat capacity? NK. Yeah, because you just take derivative with respect to U, derivative with respect to T from U, NK. And if I'm not a physicist, if I'm a chemist, because this is the way how physicists work with their systems, but we are chemists, what would be our way to represent the total energy and the heat capacity? We will use the moles, right? So then instead of K, we use a gas constant. So it would be nRT or nR. Died already. Then marker. nR for the heat capacity, right? So very straightforward, very clear way to do. And we will repeat this situation for the vibrations. As soon as we get in the partition function for the vibrations, then we will find the vibrational internal energy and the heat capacity for the vibrations. Okay, so this is pretty much what we discussed on the whiteboard. If you had the problems to see it, so I have the same formulas again. So for the partition function, we use the formula. This, by the way, I forgot to mention to you, this formula works not for any molecule, not for any case, right? It's only when ratio between temperature, which you are interested in at the given temperature, over the rotational temperature, which is determines the type of the molecule, right, dictated by the molecule itself, should be larger than 10. In other words, it's a high temperature limit, right? So the temperature is 10 times larger than the rotational temperature, which again means, why actually, what's the physical meaning of this conditions? If you not put it in the terms of rotational temperature and regular temperature. Why we need this condition? And again, think about Boltzmann distribution and population of states. Right, because at the higher the temperature, right, the more states are populated. It's enough temperature to populate high energy states. And technically, then in this case, from the sum, if you have huge number of states populated, the sum can be converted to the integral, and due to this, we were able to get this partition function in this form. But if you have really a few states populated, means the splitting in energy, rotational energy, is too big for the given temperature in T times K, if you put it in the energy unit. So then of course, you cannot really, you have to take a sum. You cannot represent sums through the integral. For this, you need really to have a huge number of states being populated. So in which case, which would be the molecule for which you for sure know that this will be not the right formula? Not heavy. Can you think about something really very, very light? The lighter molecule you cannot imagine. Helium. Anyone else? Hydrogen, H2. It would be even lighter than, well, gases would have the same mass, right? Because the mass for the hydrogen is 2, I mean, single atom is 2 due to the 1 proton, 1 electron, 2 atomic units, but H2 will have 4, right? So helium also, I think, has 4, for the, and of course it's present in 1 atomic. But for helium, we cannot talk about rotation for the helium gas, because it's a monatomic gas, right? It doesn't really have rotation at all. So the molecule, the lightest molecule will be hydrogen, and for hydrogen, it's really, we did it last time, only you can really show at room temperature, only a few states are populated, not more than 2, which means that this approximation, this formula which we used, substituting sum to the integral, will not work for the very light molecules such as H2. But if you go to the molecules constructed from the second row of the periodic table, you already actually can use this formula for the room temperature. Although if you take low temperature, right, then again you will be in a problem. That's why we really put this this condition, right? If you take in, I don't know, 10 kelvins, right, then again this condition probably will not work, and you should not use this formula. But typically, for most of the molecules, which we usually work at room temperature, this would be a good formula to use. This condition is applicable. And here is our constant which determines the molecule because of this B. Of course, it's a fingerprint of a specific molecule. I mean, fingerprint for the rotational motion for a specific molecule. It calls rotational temperature. Units are kelvins, right? And so again, applying this formula, using this as a partition function, substituting, taking the integral, we get an NKT, or just to remind you how we get an NR, number of atoms is just number of moles times a molecular number, right? And then we get in these two constants, Avogadro number times Boltzmann constant, which has a different name as a gas constant. And of course, it has a simpler numbers. We don't have this 10 to the minus 23 or 10 to the plus 23 anymore. It's 8.314 in the standard units, joules per Kelvin per mole. So here is our formula for the U, just nRT for N, and after that AT, and for the heat capacity, taking derivative with respect to T from U, right? So nR, which means, of course, does the heat capacity now depends on the type of the molecule? No, because it just depends on number of moles, and gas constant is the same for independent on the molecules. Does the rotational energy depend on the type of the molecule? But does partition function depend on the type of the molecule? Of course it does, right? Because of this B, which will be different for different molecules. So partition function depends. Moreover, whether to use or not to use this formula, you always need to check the given temperature with respect to the rotational temperature, right? Are they in these conditions, means temperature should be at least 10 times larger than the rotational temperature of a molecule. If this is right, then you're using these simple formulas for the rotational energy, for the heat capacity, and then independent on the molecule, you always will get either this for the energy, nRT, or just nR for the heat capacity. So vibrations, right? So we get into the new model, harmonic oscillator. You remember the formula for the energy for the harmonic oscillator. N plus 1/2. That's it. H nu, right? So nu is a frequency of the oscillations. Yeah. So we're using H nu n plus 1/2, right? This is again the result which you're supposed to know from the quantum mechanics. You can also represent, this is nu in a standard units. What is the standard units for the frequency? Reverse seconds or hertz, because they're the same. But again, you can think about that frequency can be taken in a wave numbers. Actually, there's a name of a wave number that you know, don't call frequency, call it wave number. So if we take it in a wave numbers, we again have in this conversion factor C, HC in front, which again, just thinking that HC is a conversion factor to get standard units for energy, means joules, if nu is given in wave numbers. And yeah, n plus 1/2, which means that when n equal, and of course n is an integer number, 0, 1, 2, 3, and so on. So the splitting between levels now is exactly the same, independent on the n, right? So it will be just h nu in between each of these states. And the lowest energy state not equals to 0, it's equals to h nu over 2. Okay, so which means that the lowest possible energy the molecule can take at the 0 Kelvin, at the absolute temperature, is not 0, it's h nu over 2. So it still has some vibrations even at the 0 Kelvin temperature. So now for partition function, we know the energy, right? So as we already said, we apply kind of the approach from the Boltzmann, where the Boltzmann distribution, where the partition function is just the normalization constant, which is represented as sum, exponent, energy divided by kT, or beta is 1 over kT. Right? And the sum goes from all states, which means that you start from the low state, n equals 0, up to the infinity. And again, this is if I represent energy in joules, if I'm using the frequency in wave numbers, which is again very typical in spectroscopy. I don't know, historically they like the wave numbers. So then again, this is a conversion factor, or you do the same thing as we did here, thinking about that you don't need this h nu if your k, if 1 over kt, if k is taken in a wave numbers, which is 0.63 something. Okay, so now we have, I simplify a little bit because this depends on n plus the term hc over 2 kt, or beta times hc over 2 would come from this term. So I took it out, right, from the sum, because it doesn't depend on the elements of the sum, doesn't depend on n. So now I need really to figure out how to take this sum, and as I already said, you probably can remember that we were working on it. I can simplify just to make this formula looks nicer. I recall this beta HC, putting it as a constant. It doesn't depend on n, right? So then I can represent this sum as just some constant n, or actually I can think it's x, now equals to the whole exponent in the power minus alpha n. And by the way, it would be less than 1 because it's negative sign for the exponent. And of course, alpha is always a positive value and n is a positive value. So you have exponent to the negative value, which means of course it will be less than 1. It's approaching approaching to 1, but always less than 1. Now, sum over this guy, right? And we represent it as 1 e to the minus alpha, minus 2 alpha, minus 3 alpha, minus 4 alpha, and so on. Right? So, which again, if I substitute my e to the x, exponent to the x, then it will be 1 plus x squared, x cubed, x fourths, and so on. So, we know how to take the sum, again, from the mass, that was the name of this expansion. So, the sum will be 1 over 1 plus x. Now, I return back to e to the minus alpha n, right? So, putting it in the bottom. And don't forget, I still have this term in front. I can return instead of alpha, I will put back this beta HC. So my final result would be this guy, which comes from this term in front of the sum, because this was just working with the sum, but I still have this term. So e to the minus beta h mu over 2, right? And then the sum goes to 1 over 1 plus exponent minus beta h in the power minus beta h c mu. Okay? So not so nice as we had for the rotations and for the well, translational probably also doesn't look that beautiful, right? The partition function for translational. But we even can do simpler. We can actually simplify this formula a little bit, but I will do it on my next slide. And again, if you don't like these notations, which, yeah, if frequency is given, you need to multiply it by C, by H, divided by KT, if temperature is given, to figure out what would be this partition function. Too many steps. It's much easier if we represent this through the, before it was rotational constant, now this is a, guess what's the name, vibrational constant, which is Hc nu over K. And again, it characterizes a molecule because this frequency of the vibrations, of course, it's an intrinsic property of a molecule, wherever the frequency it vibrates, wherever its fundamental frequencies. And the same approach, if you take K in the standard units, then you need this Hc. Or you can think that if you take, let's say, frequency is given in wave numbers, you take K in wave numbers, then you just divide frequency, wave numbers divided by frequency, or by K in the wave numbers to get the vibrational temperature. So now I can, well, this formula becomes a little bit easier. I have exponent in a power theta V, which means vibrational temperature over twice T, right? K from this beta is gone because of this K in the theta. And in the bottom part, I have 1 minus E in the power minus theta vibrational divided by temperature. So what do we call, do anyone remembers? What do we call 0 point energy? And by the way, it's not equals to 0. In the harmonic oscillator, something is called 0 point energy. Guess what is it? And it's not equal to 0. It's a low state, ground state. Good. So means it's for n equals 0. That's why I call it 0 point energy. Means 0 staying for the number of the state, ground state, the low state. So it's equals h nu over 2, right? As we said. And as we already said, if you use exactly this energy as a lowest energy of this vibrational state, then this would be the formula for the partition function. And also, I represented kind of putting this new whatever. If nu is taken in a, if nu is not frequency in a standard units, but the wave number, right? So then we need this h nu. H nu is a transition factor. So conversion factor. So, but technically we already applied this many times because we already mentioned that for us, not really the energy is important, but the difference, the change in energy. So the difference between these levels. So that's why we can really use this energy as a reference point, making it zero. And then with respect to this energy, we can talk about the energy of all other states. So let's define reference point, means this 0 point energy, being equal to zero. It's not equal to zero, we know for sure it's not. But let's take it equals to zero as a reference point. And this is what we call without 0 point energy formula, right? So then the formula will be simplified because e to the power now 0, because this energy h nu over 2 is added to 0. So then exponent in the 0 power gives you 1, right? So that's why the formula would be slightly simpler. 1 over 1 minus, this guy stays without changes, right? Minus beta hc nu, whereas nu is a great number. So in thermodynamics, this is actually our preferential form because it's simpler, and because for thermodynamics, we don't care about actual value, absolute value of the energies, since we're really talking about change in energy, or the energy with respect to some reference point, right? So that's why this is a very valid approach, and since it's simpler, that's why we follow this approach rather than taking this one. But you need to know both, because when you find out the vibrational energy, don't forget, technically, you still will have, if you set it to 0, don't forget that actual energy would be plus this term h nu over 2. So now to show that both of these ways are valid, and you really can forget about actual value of the lowest ground state, I just show you that whether you take in this partition function or that partition function, the probability of finding the population in this specific vibrational state with an index n is not affected. So in other words, we apply the Boltzmann distribution function, right? Knowing energy, knowing partition function. In first case, we apply this as a normalization constant. In the second case, we apply that as a normalization constant. So this is our Boltzmann distribution. Exponent in a power minus beta En, where En is defined by h nu n plus 1/2, with if we apply this with 0 point energy, and then QE would be this one, right? So if we use with 0 point energy, this would be our energy. This is a partition function. You can see that you can simplify it and divide by one or by this top term, and it goes to this simplified form. Now, if I do the same, but without 0 point energy, which means my energy on the top is BH nu n, not n plus 1/2, right? Because n equals 0 gives me the first term 0 now, right? And then first would be BH nu, second BH twice BH nu, and so on and so on. And now if you take this with a reference point 0, both energy 0, then the partition function also should be taken without 0 point. And again, simplifying this gives you exactly the same term, right? So which means that whether you use this partition function with 0 energy, or this partition function with the energy h nu over 2, it doesn't affect the population. It doesn't affect the Boltzmann distribution. So it's kind of a proof that both approaches are valid, but because this is simpler, of course we use mainly for your problem solution, we use this partition function. So partition function is known, then we need to follow this trend, finding the total energy and finding the heat capacity. And again, let's write it without 0 point energy, let's write it through the vibrational temperature, just because it's formula by itself easy to remember and simpler. It has less letters in it, right? So then partition function would be this in the general case. This would be in the terms of the vibrational temperature, 1 over 1 minus E theta divided by T. Of course, this is easy to remember as this has less letters. That's why this is my favorite formula for the vibrational partition function. And I still playing a little bit with applying, again, using this formula, applying another extension series, right? because I want to simplify this formula, thinking that what if I'm taking very high temperature? Means my temperature would be orders of magnitude higher than the vibrational temperature, same as was the case for the rotations. So let's see how this modifies this formula. Would it be simpler? Yes, it is. So again, this is our expansion, the expansion, which can be represented as one. If each of these terms becomes smaller, smaller, and smaller, right? So that's why only two main would be really contributing if temperature is very high, which means Q over T is really very small value, right? T is very high, much higher than theta. So then really only first two would be really important. The other ones will give you very, very small corrections. So now applying this, taking the idea the temperature much higher than the vibrational temperature, we can simplify this partition function, applying this 1 minus x, which is in our case x would be theta divided by t, right? And of course 1 minus 1, so I'm actually end up with just t over theta v. Does it look very similar to this formula? Okay. With the only difference that here we talk, don't forget, this is, of course, theta r is different from theta v because theta r is equals b, the rotational constant over k. Here is that vibrational frequency over k, if you take in both of them in negative numbers. So this simple formula is nice to use, but not very practical. Guess why? Are we really expecting that our vibrational motion for most of the molecules which we are working on satisfy these conditions for the room temperature? No? Why? Splitting between electronic levels too high, right? Much higher. It's infrared range, which is half of electron volt, right? KT is 0. KT is 250 milli electron volts, right? So we're talking about half of electron volt versus milli, hundreds of milli electron volts. So for sure, the temperature, room temperature, is not enough to populate many states at room temperature. Only ground state, probably, maybe ground, maybe 1 or 2 up, depends of course again on this frequency, on this vibrational, constant vibrational temperature. But really a few levels will be populated for regular molecules which we are working, right, in organic, inorganic chemistry, will be populated at room temperature. So that's why, although this is very nice formula, and of course your life will be much simpler if this formula can be applicable, but it's not really practical because most of the molecules not in this regime. So you really have to apply that formula, not that. But technically, if you compare, sometimes some molecules may be working this way, or maybe if temperature is given very high, 1000 kelvins, then again, you probably will be in this regime, and you can simplify your life taking this formula instead of that. But in most cases, at normal conditions, this would be the way to go. So pretty much to summarize what I already said, and comparing rotational versus vibrational partition function. So for rotations, we have this rotational constant, hcb over k, everything in the standard units except b is in right numbers. At the conditions t much larger than 10, the formula would be on a blackboard and whiteboard. So it's t divided by the sigma, which again equals 2 for comma molecule. Whatever. For the similar type of atoms in the molecule, it's 2, 1 when it's different atoms in the molecule. And at these conditions, this formula works for QR. Help me to fill this blank. So this formula for QR is what? At some special T limit. Here is high temperature limit. What is here? Valuable or true, right? Or works, applicable, right? So I have probably valuable or valid. So this formula means this formula is valid at high temperature limit. And again, high means temperature should at least time or more times larger comparing to the rotational temperature. So which means that splitting between rotational energies. Which sign is less or small? Should be smaller, much smaller actually than AT, where T represents a given temperature. And again, we usually work at room temperature. Right? So we're thinking that this is of course is the standard conditions. In most cases, in most practical cases, we will be working. So by the way, this is we also call classical regime if this is happening, because splitting is so small that you really can neglect splitting. You think that your energy is changing consistently, right? Not discrete. And yes, this is a typical case for most of the molecules. It's very rare cases, like hydrogen 2 is a good example, where this is not right. For heavier molecules, which means for any elements starting from the second row, which is actually all chemistry are mainly there. So you're really getting, and even if elements from second row and the hydrogen probably will also be already in this limit. So you're okay to use this formula at room temperature, at normal conditions. So in the same way, we're already showing that for vibrational partition function, we also can represent this as this formula at high temperature limit, right? Where QV, theta V is the vibrational temperature, defined as HC with numbers over K. And again, all these guys are in standard units. If what? Again, pretty much the same. T should be much larger than theta, or T divided by theta should be larger than 10. This formula for QV is valid at I if delta E splitting between levels, again, less than KT, which again would be a classical regime. Unfortunately, and here's a big difference, this is not practical. This is not a regular case for most of the molecules. This is not right. And you really need to go to thousands. Still have 10 minutes. So we usually you need really to go to probably more than 1,000 kelvins, really very, very high temperatures, to reach this limit for regular molecules. But iodine 2 has its vibrational temperature 300 kelvins. Then the question to you: if iodine 2 has a frequency, vibrational temperature 300 kelvins, means theta E is 300 kelvins for iodine 2. Could you use this formula? Still not. It's equals, but it has to be 10 times larger, right? So then at which temperature this would be applicable for iodine 2? We're getting again back to the thousands, right? Even for the very heavy molecules where we have kind of this set, but for most of molecules, this set of vibrational would be 20,000, 2,000, 3,000 right away for the molecules, right? So of course, it's beyond the regime of the room temperature. So that's why this formula is not very much useful, not very much valid for us. But it exists. Okay, so now we getting the internal energy for taking the derivatives, right, from the partition function. And again, well, log. In this case, I think actually, I think we will not use one, like we can use this formula, right? Or you can take log and then take a derivative with respect to beta. So I think in this case, it's probably easy to do it this way, taking log of this formula, right? And then take a derivative, or maybe not. No, I still getting with the same idea. So we take in 1 over q, derivative from q, right? Which means you need just to take a derivative from 1 minus e to the power, whatever, constant beta with respect to beta in the power minus 1. The derivative would be minus 1 goes in front, right? And then we take a derivative from exponent. This constant goes also in front with also negative sign, right? And exponent stays in a power where it was. So we get in this as, and this, by the way, this power will also go to minus 2. We get in this, and this coefficient which we get in front when taking this derivative, of course we still need to have this n. We need to divide, this is already divided, 1 over this guy goes up with a positive sign. So after doing all this, this would be the formula, right? Then simplifying this guy, doesn't look very simplified. So we have n, the coefficient a, which is h nu, we have here HCU, with numbers, right? And the same in the power for HCU with numbers. Slightly simplifying it, multiplying by exponent, top and bottom can be multiplied by this exponent, right? So then this exponent is gone, and we get in, this is kind of changing the sign if you multiply by the exponent in a positive power, right? So then this would be 1 over this guy, and this just gives me -1. So this is how we get in this n constant, e to the constant beta with a plus sign, by the way, right? -1. So this is also right. But in books, and I don't think it's much harder than this, but in books they prefer this form rather than that. And again, to get this, you just need to multiply top and bottom by the exponent with the same power but with a positive sign. So here would be the final formula for the vibrational energy. You can see it's pretty nasty in the sense that it has many terms and it's really exponent. Yes, unfortunately, vibrations, the formula for the vibrational energy looks more complicated than for translational and rotational. And again, because we are not in a classical regime of molecules, so we really have to calculate this formula, if you really need to calculate it. If the vibrational temperature is given, or you can define vibrational temperature when the frequency is given to you, then the formula, I think it's again easy way to remember because it has less letters, right? Can be represented in this form, or we can convert it from total number of particles to the moles. So it will have nr zeta, vibrational, divided by exponent zeta over t minus 1. Don't forget, we were using the partition, well, here we're using the partition function without zero energy, thinking that reference point of energy equals to 0, which is not, right? So this is energy without 0 point. Actual energy with 0 energy, right, need to include this first term, h nu over 2, right, times number of particles for each of the molecules. So, and if you put it in the terms of zeta, it would be nk or nr zeta over 2 plus the same term as you have here. So you need to add this additional term because your loss energy has some value, not 0. But again, for thermodynamics, it's not very important for us. So we even use this as internal energy for the vibrations, because again, we usually not interested in the energy by itself, but in the difference between energy. And then this guy will be gone. So this is good enough to remember. So the heat capacity for diatomic molecules, now we know the partition function, which doesn't look very easy, very simple as this case, so means the derivative from temperature also will be not easy to take. So we need to take a derivative from this guy, which not very hard, but again, the derivative from e to the -1 in the power -1, right? So getting, if you really take this derivative, getting this to the -2, taking this squared, and this term goes up, and the derivative, this exponent stays, with some coefficients getting in front, right? So, and now putting this in a form of vibrational temperature, we get in nk, kind of little bit simple form, nk vibrational over t squared, and then exponent zeta over t over the exponent zeta over t minus 1 squared. And you have to calculate all this when you really work, because unfortunately, yeah, vibrations not in a classical regime, and the formula becomes more complicated. You have to really calculate. But if you're lucky, if temperature is very high, which is not the case, or the molecule really having very, very, very low vibrational temperature, which also usually not the case, your results would be simpler. It would be just the same as we got for the rotational heat capacity, Nk or Nr. But again, this is not very much applicable because usually you're not in this regime for the room temperature and for more physical. You have to really do some calculations with this formula. And that formula is the formula for the U, which is this. Okay? So vibrations really is a thing which requires some work to do, while when you talk about energy and heat capacity, while translational and rotational is really a piece of cake because it's 3/2 R for the heat capacity and just NR for the heat capacity for rotations. We have a little bit time. I think one of your problems from the homework, having this question about the population of the vibrational state, and it's really based on the idea that again, the question is where you're getting these vibrational temperatures and rotational temperatures. From spectroscopy, from vibrational spectroscopy and rotational spectroscopy. But of course, there's some coupling between rotations and vibrations. Although we say that they are in very different regimes in their frequencies and their energies, but of course, you can completely forget that they can feel each other, that they really interact. So there's vibronic spectra, when you really kind of take into account both vibrational and rotational degrees of freedom. The vibronic spectra looks like that. It's really kind of symmetric with respect to this 0 point. 0 is really where you have the lowest frequency, the fundamental frequency of your molecule, pure vibrational frequency. So it means where you have, like, you get, this is you can get from experiment, right? This middle point will give you immediately the fundamental vibrational frequency, which you can use to figure out what will be your vibrational temperature. And then the splitting, and then you see this kind of nice sharp peaks, and this with very similar splitting between them, right? And pretty symmetric from right and left. So the splitting between these peaks is B, the rotational constant. This is how you can measure the rotational constant from molecules, and if you know rotational constant, you can figure out what is your rotational temperature. And now, this height of these sharp peaks telling you how many states are populating the rotational J equals 1, 2, 3, 4, and so on. Right? Actually, it's from 0 to 1. This would be population of the first state, second state, and so on, rotational state. And you can see that we get into some maximum, right, and then it's going down. So we really have a nice distribution. This is taking at room temperature. You definitely have more than this one rotational state populated, many of them, maybe 10, maybe 20, maybe 70, but then it's going down. So our goal, and just to remind you, this is how we do with finding the population using the Boltzmann factor, right? Don't forget, we do have degeneracy, and degeneracy in this case really growing very quickly linearly with the number of the state. So it means degeneracy of that state is much bigger than degeneracy of the second and third state. And it's also contribute to the more population. It means really population of the states become higher. And the partition function for the rotations, which we already know. So substituting all this, right? And then we want to know what would be the maximum J populated at, let's say, this specific temperature. Which means we need to find the maximum from this function with respect to G. How do we find the maximum of the function? Derivative and set it to 0. Exactly the same what we do here. So this is our function, we need to find this maximum. So which means we are taking derivative, set it up to 0, right? So I'm putting it in occupation numbers. You can talk about probabilities, or you can say it's occupation numbers. Pretty much the same formula with just number of molecules, right? Finding derivative from the occupation number. If you solve it, well, again, you're substituting this Hg based on the Boltzmann factor, the partition function. If you really solve it, we get in the formula for the temperature, right, with whatever J. Let's say this is a J, 1, 2, 3, 4, you calculate 9, you can figure out what would be the temperature taken when this factor is taken in this experimental factor. And of course, backward. If temperature is given, you can figure out what is your maximum J based on this formula, solving the quadratic equation in the opposite way. You might find this formula useful for your homework, and that's why actually I'm showing it. And of course, this is completely correlated to everything which you already learned, the rotational partition function, the Boltzmann distribution, which we are using all the time, starting from the week number 3 in the semester so far, right? And yeah, knowing some calculus features, you can find the maximum of the function, just set it to 0, right? Set it to 0, and and solve it for temperature. You just put your final formula. So you don't need to do this derivation. You just take the formula when you work on your homework, whatever it is, of the mate, or whatever the number is. And just want to remind you, sorry, I'm already overusing a little bit of the time. Remind you, if you, how many people didn't solve, need help with the homework too? First part. You don't? You good? How many people ready to give it to me right now for the bonus point? Right? I can take it. If not, you still have a lot of time. But if you're close to finishing, really finish it, don't forget you need this time for working on the part 2, which is, again, time-consuming, pretty much the same story, but now you need to apply it to the polyatomic molecules. You can have a name. Are you having your name in? Okay. At least you don't put your name on all the pages, because I want to do the peer evaluation for this case. So thank you very much for helping me to open 11 a.m. spot, because it's really important for me. And see you Friday at 11, right, in our regular place. So you right. I can say Levi that he doesn't need to worry to come.
Yes.
At 11. Okay, good. Thank you. Thank you. Bye-bye.